Welcome to Sapiens Untold. If you enjoy these explorations of humanity's mysteries, please like and subscribe. Where are you listening from tonight? It is twilight, and you stand in a quiet earthly field, gazing upward. Above, Mars glows a steady, distant ruby against the deepening indigo sky. For millennia, this celestial neighbor has sparked wonder, but modern planetary science reveals a profound secret it may hold: the story of our own origins, perhaps even before Earth itself was ready for life. You begin to contemplate a controversial hypothesis, steeped in mounting scientific evidence. What if Mars hosted life, and possibly sophisticated life, before our planet was habitable? You imagine Mars as it once was, billions of years ago. Geological timelines show that Mars, though smaller than Earth, cooled and solidified at a much faster rate. Planetary science reveals that our scarlet neighbor may have become a warm, wet world, ideal for liquid water, potentially 500 million to a billion years before Earth's surface had sufficiently cooled from its molten, hostile state. During this critical period, while early Earth was still a hellish sphere, bombarded by asteroids and too hot for stable liquid water, early Mars was a comparatively gentle paradise. Rover data indicates this early Mars between 4 and 3.5 billion years ago boasted flowing rivers and standing lakes, possibly even oceans. Ancient Martian river deltas and lake beds, like those explored by the Curiosity rover and now Perseverance in Jezero Crater, prove liquid water existed for extended periods, etched into landscapes billions of years old. Atmospheric isotope ratios and geological evidence prove Mars once held a thick atmosphere, capable of sustaining these vast water bodies and moderate temperatures, perfect conditions for life to emerge. Then, you consider the most intriguing evidence: the Martian meteorites. Meteorite analysis suggests rocks ejected from Mars by powerful asteroid impacts, some of which have journeyed across the solar system to land on Earth, contain organic compounds, the building blocks of life. ALH84001, a meteorite from Mars, famously contained microscopic structures resembling fossilized bacteria. If life existed on early Mars, it demonstrates a pathway for that life to travel. We might not be searching for alien life on Mars, but rather searching for our own ancestral home. You feel the chill of the evening air as you continue your vigil, Mars now a bright beacon against the deep velvet sky. What secrets does that distant light hold beyond the tantalizing clues from meteorites? Planetary science reveals a dramatic saga of planetary transformation. Rover data indicates that Mars was once vibrant, teeming with the ingredients for life. The Curiosity rover, exploring Jezero Crater, discovered complex organic molecules preserved within 3 billion-year-old mudstones. It also detected mysterious fluctuations in atmospheric methane, which some scientists speculate could be a biosignature, a hint of current biological processes deep beneath the surface. Geological evidence proves these ancient lakes persisted for thousands, even millions of years, ample time for life to emerge and evolve. Now, you turn your attention to the Perseverance rover, diligently collecting samples within Jezero Crater. This site once hosted a vast river-fed lake, and its sediments are prime candidates for preserving ancient Martian microbes or the biochemical traces they left behind. These samples, destined for return to Earth, promise to provide definitive answers about whether life ever existed there. Yet, what happened to this once habitable world? The atmospheric mystery unfolds. Geological evidence proves Mars once possessed a thick atmosphere, sustained by an early magnetic field. However, this field collapsed, leaving the planet vulnerable. Atmospheric isotope ratios reveal the tragic story. The relentless solar winds stripped away Mars's protective blanket over millions of years, transforming it into the cold, dry, barren world we observe today. For that critical first billion years, however, Mars was a veritable paradise compared to the hellish, still-forming Earth. This planetary catastrophe leads to a profound question. If life had not only emerged but thrived on early Mars, could it have found a way off the planet? The theory of panspermia suggests an extraordinary answer. Asteroid impacts on Mars could have ejected rock fragments into space, some carrying microscopic life. We possess over 200 known Martian meteorites on Earth, proof that such interplanetary transfer is entirely possible. Microbes, shielded within the rock interiors, could survive the harsh vacuum of space and the fiery entry through Earth's atmosphere. If life existed on Mars 4 billion years ago, these hardy Martian travelers might have seeded our then habitable Earth, making us perhaps the descendants of Martians. We are, in a sense, searching for our own origins. You close your eyes, imagining not the silent vista of Earth, but the thin, ethereal air of Mars. Through the marvel of modern engineering, you can almost hear it. The faint, rustling whisper you discern is not a distant earthly breeze, but the actual Martian wind, captured by Perseverance's microphone in Jezero Crater. This is the sound of a world that, billions of years ago, might have been very much alive, its atmosphere then thick enough to carry the rush of ancient rivers and the lapping of waves. Today, Perseverance continues its meticulous investigation, crawling across sediments that once formed an expansive river delta, feeding a long-gone lake. Planetary science reveals that this region held stable liquid water for thousands to millions of years, an immense span of time perfect for life to take root and flourish. You visualize the rover's instruments analyzing ancient mudstones and clays, searching for definitive biosignatures, the indelible chemical or structural traces left behind by living organisms. If life existed here, its fossilized remains or biochemical fingerprints might be preserved within these very rocks. The geological evidence proves Mars possessed the essential ingredients: liquid water, energy sources, and organic molecules. Curiosity rover data previously indicated the presence of organic molecules in similar ancient mudstones. Now, Perseverance seeks direct proof that these molecules were indeed part of a living system. Imagine the moment if these return samples reveal unambiguous signs of microbial life, dormant for eons, waiting for our discovery. This would not only confirm life beyond Earth, but validate the incredible timeline paradox: Mars offering a fertile cradle for life 1 billion years before Earth was ready. This scientific quest extends beyond mere microbes. The timeline, Mars being habitable for such a vast period before Earth, invites a deeper, more speculative contemplation. If life emerged readily under such conditions, could it have evolved beyond simple forms? Mainstream science cautiously explains controversial satellite imagery, such as the famous Face on Mars in the Cydonia region, as natural geological features, an optical illusion, or pareidolia. Yet the question lingers: if Mars hosted life for 1 billion years, could intelligence have evolved before the catastrophic atmospheric loss? The concept remains highly speculative, but the underlying scientific plausibility of early Martian microbial life is what drives this relentless exploration. We are not just asking, could Mars have had life? We are now asking, where is the proof? You stand now in a boundless, cold panorama, Utopia Planitia, one of the largest impact basins in the solar system, where the Viking 2 lander once settled. The atmosphere here is thin, dry, and unforgiving, a stark contrast to the vivid, warm Mars envisioned 4 billion years ago. This vast, silent plain, with its ancient weathered rocks, silently bears witness to the planet's dramatic loss of habitability. It is a sobering testament to a planetary catastrophe, where a thick, life-sustaining atmosphere proven by isotope ratios and geological evidence of ancient rivers, was stripped away by solar winds after Mars's magnetic field collapsed. Mainstream planetary science largely agrees that while early Mars was undeniably habitable and likely harbored liquid water, definitive proof of ancient Martian life remains elusive. The organic molecules found could be abiotic, and methane fluctuations might be geological, not biological. Yet the possibility that Mars hosted microbial life first, 500 million to a billion years before Earth was ready, is considered scientifically plausible and actively drives our current Mars exploration missions. These missions, particularly those designed for sample return, aim to provide those definitive answers. But what if the story runs deeper? The idea that Mars could have not only hosted life but evolved it to intelligence before its atmospheric demise opens a more controversial, yet equally profound, line of inquiry. You recall the enigmatic geometric formations some claim to see in regions like Cydonia, or the famous face on Mars, features that, while explained by mainstream science as natural geological formations or pareidolia, stir the imagination. Could an advanced Martian civilization, observing their world's slow death, have attempted to preserve knowledge, terraform other worlds, or even migrate? The philosophical implications of such discoveries are immense. If life arose independently on Mars before Earth, it proves that life emerges readily under the right conditions, suggesting the universe teems with it. If Earth was seeded by Mars, we are, in essence, Martian descendants exploring our ancestral home, an astonishing origin story. And if intelligence evolved there, we might discover their ruins, their libraries, or even warnings about planetary death encoded within their artifacts. These are the profound questions that linger as you survey the cold, still panorama of Utopia Planitia, pondering a past that could redefine our future. You drift above the rust-colored expanse of Mars, not in a physical spacecraft, but through the sweeping gaze of orbital imaging. Below you, across the planet's vast northern plains, you trace the subtle, almost imperceptible undulations of what planetary science reveals as the ghost of an ancient shoreline. This is not a fleeting pool, but the probable remnant of an immense Martian ocean, perhaps billions of years ago. Imagine the glint of sunlight off liquid water, stretching across what is now arid desert. Geological evidence, including specific mineralogical signatures observed from orbit and the geomorphological features resembling ancient coastlines, powerfully suggests that this region once held significant bodies of standing water, potentially covering a third of the planet. This orbital perspective offers a profound counterpoint to the desolate Mars we see today. It strengthens the timeline paradox. While Earth was still a molten, uninhabitable sphere 4 billion years ago, Mars was a world of rivers, lakes, and potentially oceans. These conditions, stable over hundreds of millions of years, would have provided an incredibly fertile environment for life to emerge, far more extensive than the localized lakebeds currently explored by rovers. Such vast aquatic environments significantly increase the probability that life not only arose but thrived on early Mars, long before Earth's surface cooled enough for its own primordial seas. The question then expands beyond mere microbial existence. If life were widespread in these Martian oceans, the likelihood of complex ecosystems developing, even if simple, becomes more plausible. And with a billion-year head start on habitability compared to Earth, the implications for panspermia become even more compelling. Asteroid impacts on an ocean-bearing Mars could have ejected countless water-laden rocks into space, a far richer source for potential life transfer to early Earth than dry, barren land. Mainstream planetary science overwhelmingly accepts the evidence for a past wet Mars, complete with a thick atmosphere proven by atmospheric isotope ratios, which later collapsed, due to the loss of its magnetic field. What remains to be definitively proven is the existence of life itself within these ancient oceans. The samples being collected by Perseverance in Jezero Crater from what was once a river-fed lake are the closest we have come to directly probing such environments. As you drift above these ghost shorelines, you ponder, if we find definitive proof of life within those ancient Martian waters, are we merely confirming alien life? Or are we tracing the very currents that carried our deepest ancestors to a nascent Earth? You stand before a magnificent, silent amphitheatre of time, the dried-up Eridania Basin in Mars's southern hemisphere. Here, the landscape reveals an ancient, layered history, a geological diary written in sediments. You run your gaze along the exposed cliffs, witnessing the subtle stratifications, each band a record of eons gone by. Planetary science reveals that this immense basin once held a deep, expansive sea, perhaps 3.7 billion years ago, far deeper and more enduring than many of the smaller lake systems. Geological evidence proves these sediments formed underwater, accumulating layer upon layer for millions of years, indicating a prolonged period of stable liquid water. Imagine the sheer volume of water that once filled this colossal basin, fostering an environment where life could not only emerge but thrive and diversify. The stable conditions, persistent for such an immense duration, represent a prime location for the preservation of ancient biosignatures, far beneath the punishing surface. If life developed anywhere on early Mars, these deep, long-lived aquatic environments offer the best chance of finding its fossilized traces or complex organic molecules. These findings would further strengthen the timeline paradox, a vibrant, water-rich Mars existing when Earth was still largely a hostile, molten world. This prolonged period of Martian habitability, a critical 500 million to a billion-year head start, dramatically elevates the plausibility of panspermia. If early life on Mars inhabited such vast seas, asteroid impacts could have ejected waterlogged rock fragments, rich with microbial cargo towards Earth. These journeys, enduring for millions of years, are proven possible by the Martian meteorites we've discovered. Life, shielded deep within these rocks, could have survived the harsh cosmic radiation and fiery atmospheric entry, arriving on a nascent Earth ready to be seeded. Mainstream planetary science robustly supports the past existence of extensive water bodies like the Eridania Sea, and the possibility of ancient microbial life on Mars is a central driver for missions like Perseverance. The quest is no longer, could Mars have had life? But where is the definitive proof? As you absorb the silent grandeur of these ancient sediment layers, you are left with profound questions. Are these just geological formations, or do they whisper of a distant, living past? And if we find life preserved within them, what profound truth will that reveal about our own place in the universe and the ultimate origins of life itself? You stand with the Curiosity rover at the foot of an ancient alluvial fan in Jezero Crater, a sprawling apron of sediment deposited by flowing water billions of years ago. The fine Martian dust whispers around your boots, carrying echoes of an unimaginable past. You observe the layered rock formations, clearly visible strata that planetary science interprets as unequivocal evidence of long-gone rivers carving paths across the Martian landscape, emptying into a vast lake that once filled much of Jezero Crater. Geological evidence proves the existence of sustained liquid water, vital for life's emergence. Imagine the sheer volume and persistence of these ancient waterways. Rover data indicates that this lake existed for thousands to millions of years, not merely as a transient puddle, but as a stable, habitable environment. This is a critical piece of the timeline paradox. While early Earth was still too volatile for such stable aquatic systems, early Mars presented a calm, watery cradle. Curiosity's groundbreaking discovery of organic molecules, the very building blocks of life, within these 3 billion-year-old mudstones here in Jezero Crater, sent ripples of excitement through the scientific community. While these molecules could have been formed by abiotic processes, their presence in such a clearly habitable ancient environment is deeply suggestive. Further intrigue arose from Curiosity's detection of mysterious methane fluctuations in Mars's atmosphere. These spikes, appearing seasonally, could potentially hint at active biological processes occurring beneath the surface, a tantalizing prospect that suggests life might not just be a relic of the past, but an enduring whisper in the present. Mainstream planetary science actively investigates both biological and geological explanations for this phenomenon, balancing rigorous skepticism with open-minded curiosity. The existence of such a long-lived, water-rich environment in Jezero Crater bolsters the panspermia hypothesis. If life were present in this ancient Martian lake, asteroid impacts could have ejected fragments of these life-laden sediments into space. We know such rock transfer is possible. Over 200 Martian meteorites have been identified on Earth. These ejected rocks, acting as interstellar transports, could have carried Martian microbes to a burgeoning Earth, seeding our planet with foreign, yet familiar, genetic material. As you look out across the ancient alluvial fan, you wonder if you are standing not just in a crater, but at the potential source of life on Earth itself. You kneel in a dry Martian streambed, reaching out to touch the smooth, water-worn pebbles. The sensation is startlingly familiar, a testament to the universal power of erosion. Planetary science reveals that these rounded stones, discovered by the Curiosity rover in Jezero Crater, are not angular fragments of impact ejecta, but telltale signs of sustained flow by liquid water. Geological evidence proves these pebbles were shaped by ancient rivers, tumbling and grinding for extended periods, a process indistinguishable from riverbeds on Earth. This direct, tactile evidence of ancient flowing water is profound. It firmly places early Mars in a category of its own during the critical period when life was first emerging in our solar system. While Earth was still a hostile, largely molten sphere undergoing heavy bombardment, these Martian rivers flowed, delivering vital nutrients and shaping a landscape capable of fostering life. Mars had a critical 500 million year head start on habitability, a window of opportunity for life to emerge and perhaps even flourish. The implications for panspermia, the theory of life traveling between planets, are amplified by these findings. You consider the mechanics. Massive asteroid impacts on a wet, river-laced Mars could have ejected chunks of these very streambed rocks into space. Within these rocks, shielded from radiation and the vacuum, microbial life could have survived. We know this transfer is possible, as over 200 Martian meteorites have been identified on Earth, proving that planetary material can indeed travel between worlds. If Mars harbored life 4 billion years ago, these river-worn pebbles could have been tiny ark-like vessels, transporting Martian microbes to a nascent Earth. This scenario suggests a truly profound origin story for terrestrial life, that we, ourselves, might be descended from these ancient Martian travelers. The question then shifts from merely, did life exist on Mars, to, are we Martian descendants exploring our ancestral home? Most planetary scientists accept the overwhelming evidence for early habitable Mars, and the possibility of ancient Martian microbes is actively investigated. Yet, the definitive proof of Martian life, whether in these smooth pebbles or the samples being collected by Perseverance, remains the driving mystery. As you feel the texture of these ancient stones, you wonder if you hold in your hand not just a piece of Mars, but a tangible link to the genesis of all life on Earth. You find yourself transported back to a tense 1976 mission control room, the air thick with anticipation. The rhythmic hum of distant machinery and the hushed murmurs of scientists create an atmosphere charged with hope and uncertainty. On Mars, 2 Viking landers have successfully touched down, carrying the hopes of humanity to discover life beyond Earth. You gaze at the glowing screens, awaiting a signal that could redefine our place in the cosmos. The Viking missions were designed with a singular, audacious goal: to directly search for signs of life in the Martian soil. The landers carried 3 sophisticated biology experiments: the gas exchange, pyrolytic release, and the labeled release experiment. You watch as data begins to trickle in from the labeled release. This experiment involved adding a nutrient-rich chicken soup to Martian soil samples, designed to detect metabolic activity by looking for radioactive gas released by potential microbes. The initial results were startling: a distinct positive signal consistent with biological processes suggesting active metabolism within the Martian soil. A wave of hushed excitement, then cautious optimism, spreads through the room. However, the jubilation was tempered by data from another instrument, the Gas Chromatograph Mass Spectrometer, or GCMS. Planetary Science reveals this instrument, designed to detect organic molecules, the very building blocks of life, found none in the same soil samples where the labeled release experiment hinted at activity. This created a profound paradox. If life was present, even microbial, it should leave behind organic residues. Mainstream science attributed the labeled release's positive result to unusual abiotic chemical reactions in the Martian soil, perhaps involving peroxides rather than living organisms. Yet, the controversy persisted. Some researchers maintained that the Viking experiments, though groundbreaking, might have been too limited or even accidentally sterilizing. They questioned whether the GCMS was sensitive enough to detect trace amounts of organic compounds, or if the soil samples represented the planet's true biological potential. This early, inconclusive search profoundly shaped future Mars exploration, proving the planet was far more complex than initially thought. As you consider this historical moment, you recognize it as the beginning of a larger journey, a deepening inquiry into a world that, even then, was whispering secrets of a once habitable past. You stand in a simulated Martian environment, observing a replica of the labeled release experiment. You watch as a soil sample, representing the dry, rusty regolith of Mars, is introduced to a droplet of nutrient-rich solution. An initial, surprising gasp of radioactive gas, a positive result, is precisely what occurred on Mars decades ago. This tantalizing signal, detecting metabolic activity, sparked immediate hope. Could this be proof of life, breathing its last on a dying world? This gasp of air remains one of astrobiology's most profound enigmas. The experiment's design was ingenious. If living microbes were present in the Martian soil, they would consume the radioactive nutrients and release tagged gaseous byproducts. The initial positive detection was then followed by a control. A second sample was heated to sterilize it before receiving the nutrient solution. Planetary Science reveals that this heated sample showed no activity, a result that, on Earth, would strongly suggest biological processes. Yet, the lack of organic molecules detected by the Vikings' gas chromatograph mass spectrometer in the same soil presented a paradox. Mainstream science largely concluded that a non-biological oxidant in the Martian soil was responsible for the chemical reaction, mimicking life without actually being alive. However, some scientists continue to ponder this perplexing outcome. They suggest that perhaps the sterilizing heat was too extreme, or the GCMS was simply not sensitive enough to detect trace amounts of organic material from a sparse microbial population. The possibility remains that the labeled release experiment genuinely detected a faint, lingering whisper of extant Martian life. This lingering uncertainty underscores the profound importance of Mars's earlier history. Geological evidence proves Mars once harbored conditions ideal for life for millions of years, far predating Earth's own stable environments. If Mars truly harboured life, even microbial, that early and abundantly, then the labelled release anomaly might not have been a chemical fluke, but a fleeting metabolic cry from an ancient lineage. As you ponder this enduring mystery, the labelled release experiment becomes a symbol of our persistent quest. Was that a chemical reaction, or a genuine biological sigh from a world that had a billion-year head start on hosting life, a world that could have seeded Earth through panspermia? The question still echoes across the vast emptiness between our worlds. You feel the biting chill of an Antarctic wind whipping around you, stinging your cheeks with ice crystals. The vast white expanse stretches endlessly, a desolate beauty perfectly preserving secrets from the cosmos. It's December 27, 1984, the day the meteorite ALH84001 was found in the Allen Hills. You run your gloved hand over its dull, dark surface, a humble rock weighing just over 4 pounds, unaware that it holds a controversy that would ignite the world of astrobiology over a decade later. This meteorite is a piece of Mars, hurled into space by an ancient asteroid impact and eventually making its way to Earth. Meteorite analysis conclusively proved its Martian origin through unique gas compositions matching Mars's atmosphere. Then, in 1996, the scientific community erupted. Researchers announced the discovery of microscopic structures within ALH84001 that resembled fossilized bacteria, along with organic molecules and mineral compounds often associated with biological activity. You peer into the magnified image of these structures, resembling tiny segmented worms, and feel the thrill of that initial, breathtaking possibility, proof of ancient Martian life. This discovery profoundly reinforced the timeline paradox. Planetary science reveals that ALH84001 crystallized from molten rock about 4.5 billion years ago, then experienced a period of water alteration approximately 4 billion years ago, precisely when Mars was wet and Earth was still largely molten and hostile. This meteorite offered a tangible link to Mars's early habitable period, a potential window into a time when life could have flourished on our neighbouring world. Mainstream scientific debate, however, quickly presented alternative explanations. While the evidence was compelling, scientists cautioned that the structures could be mineral formations mimicking biology, and the organic molecules could have formed through abiotic, non-biological processes, or even been terrestrial contaminants. The possibility of ancient Martian microbes remains scientifically plausible and a significant driver for Mars exploration, but definitive proof from ALH84001 continues to be debated. Nevertheless, this single rock transformed the search for life beyond Earth, shifting it from mere speculation to a tangible, evidence-based quest. As you consider ALH84001, you realize its true legacy isn't just a potential fossil, but the profound questions it forced us to ask about our place in the universe. You lean forward, peering intently into the cool, glowing eyepiece of a high-powered electron microscope. Before you, magnified thousands of times, is a thin sliver of ALH84001, the meteorite from Mars. The silence of the laboratory is absolute, broken only by your own breath. You begin to resolve minuscule rod-shaped structures embedded within ancient carbonate globules inside the rock. These are the controversial nanofossils, so tiny they challenged conventional understanding of microbial size, yet strikingly reminiscent of fossilized bacteria found on Earth. You trace the contours of these minute forms, some appearing segmented, others ovoid. Meteorite analysis in the 1990s, when these were first identified, also revealed tiny grains of magnetite and other mineral compounds within these globules. On Earth, similar mineral assemblages are often produced by magnetotactic bacteria. Furthermore, the meteorite contained polycyclic aromatic hydrocarbons, a type of organic molecule frequently associated with decayed biological matter. The cumulative evidence sparked immense excitement. Could these be the fossilized remains of ancient Martian microbes, preserved for billions of years? This microscopic view opens a window to Mars as it was 4 billion years ago. Planetary science reveals that this was a period when ALH84001, then part of the Martian crust, was saturated with liquid water, precisely when Mars was a warm, wet world. During this critical window, Earth was still a hostile, molten sphere, frequently bombarded and inhospitable to stable liquid water or emerging life. Mars, with its vast oceans and flowing rivers, had a 500 million year head start on habitability. However, mainstream science, while acknowledging the intrigue, also presented alternative interpretations. The structures could be mineral precipitates, forming under unique Martian geological conditions, merely mimicking biological shapes. The organic compounds, while present, could have formed abiologically, or even been terrestrial contaminants introduced after the meteorite's arrival on Earth. The debate, rigorous and essential, highlights the immense challenge of proving extraterrestrial life. Yet, ALH84001 undeniably proves that rock samples can travel from Mars to Earth. If these enigmatic structures were indeed biological, then the panspermia mechanism is powerfully underscored, a direct pathway for Martian life to have potentially seeded our own planet. As you pull back from the microscope, the tiny ambiguous forms within the rock leave you with a profound sense of wonder, a miniature mystery at the heart of our origins. You are now in a hushed observatory, not on Earth, but in the virtual space of our scientific instruments, mapping the thin Martian atmosphere. You focus on an invisible, transient phenomenon, the plumes of methane gas detected remotely from Earth and, crucially, by the Curiosity rover on the surface. This gas, barely a trace, appears to spike seasonally, like a faint breath exhaled from a slumbering world. This elusive signature, barely detectable, yet undeniably present, poses one of Mars's most tantalizing mysteries. Rover data indicates that Curiosity has consistently measured these localized rhythmic fluctuations of methane. This is significant because, on Earth, the vast majority of methane is produced by biological processes, often from microbial life. The seasonal nature of these spikes further adds to the intrigue, suggesting a dynamic process at play beneath the surface, possibly influenced by temperature changes or subsurface water cycles. Planetary science rigorously investigates whether this could be a biosignature, a direct hint of extant, living Martian organisms. However, mainstream science also explores compelling geological explanations. Methane can be produced abiologically through hydrothermal activity, serpentinization, a reaction between water and certain rocks, or even from trapped ancient methane ice released seasonally. The challenge lies in unequivocally distinguishing between these biological and abiotic sources. Yet, the persistent detection and its rhythmic nature keeps the biological hypothesis alive and actively investigated. This invisible gas, therefore, represents a potential bridge between Mars's habitable past and a potentially living present. The connection to Mars's earlier history is profound. If current methane emissions are biological, it implies that life, which might have arisen during Mars's 500 million year head start on habitability, survived the catastrophic atmospheric loss and adapted to the subsurface. Geological evidence proves that early Mars had rivers, lakes, and a thick atmosphere, conditions ideal for life to emerge. If that life persisted, hidden beneath the surface, then the implications extend to panspermia. Could ancient Martian microbes, transported to Earth, have descendants now exploring a planet that still harbors its own subtle, invisible breath of life? This seasonal methane, this transient whisper, compels us to listen more closely to our red neighbour. You sit in a university laboratory at midnight, surrounded by the quiet hum of analysis machines and the soft glow of data screens. On one monitor, charts display the curious, fluctuating lines of Martian atmospheric methane, a whisper from our neighbouring world that refuses to be silenced. This invisible gas, detected by the Curiosity rover, poses one of the most profound and hotly debated questions in astrobiology. Is it a byproduct of geology or a sign of life, even now, on Mars? You lean closer, observing the data patterns. Rover data indicates distinct seasonal spikes in methane concentration, localized within Jezero Crater. On Earth, the vast majority of atmospheric methane is biological in origin, produced by microbes. The periodic nature of these Martian emissions naturally leads to a powerful speculation. Could this be a biosignature, a breath from active subsurface microbial communities hidden from the harsh surface radiation? If life did arise on Mars during its 500 million year head start on habitability, perhaps it retreated underground as the planet's atmosphere withered, adapting to the subsurface niches. However, mainstream planetary science rigorously explores alternative, abiotic explanations. Geological evidence points to processes like serpentinization, where water reacts with iron-rich rocks to produce methane. Another possibility involves the periodic release of methane trapped in clathrates, ice-like structures beneath the surface, as seasonal temperatures fluctuate. The challenge, you realize, is immense. How do we unequivocally distinguish a geological gasp from a biological sigh, especially when our instruments are limited and our samples are few? The debate over Martian methane's origin is at the forefront of astrobiological inquiry, a microcosm of the larger quest to understand Mars's potential for life. If proven biological, this transient gas would fundamentally shift our understanding of life's resilience and its prevalence beyond Earth. It would also strengthen the panspermia hypothesis, suggesting that if life endured on Mars, its ancient ancestors could have easily travelled to a young, fertile Earth. As you consider these competing hypotheses in the quiet of the laboratory, the invisible methane becomes a potent symbol, a persistent, enigmatic question challenging us to unravel Mars's secrets, and in doing so, perhaps discover a deeper truth about our own origins. You hear the gentle whir of the drill, a sound of precise engineering echoing across the silent, ancient landscape of Jezero Crater. You stand beside the Curiosity rover as its drill bites into a clay-rich mudstone, a rock formed from fine sediments deposited billions of years ago. This isn't just any rock. Planetary science reveals these mudstones are remnants of a vast lake that once filled Jezero Crater, a body of water that persisted for thousands to millions of years. Geological evidence proves that liquid water was stable and widespread here, a stark contrast to the molten, hostile Earth of the same era. The material extracted by Curiosity's drill led to a groundbreaking discovery: the detection of complex organic molecules within these 3 billion-year-old mudstones. You imagine the thrill of the scientists as rover data indicated the presence of these carbon-based compounds, the very building blocks of life as we know it. These molecules, preserved deep within the rock, survived eons of radiation and the planet's atmospheric loss, offering a tantalizing glimpse into Mars's potentially living past. This finding dramatically reinforces the timeline paradox. Early Mars, cool enough for stable liquid water and equipped with a thick atmosphere, proven by atmospheric isotope ratios, had a 500 million to 1 billion year head start on habitability compared to Earth. During this critical period, Mars was a thriving world where organic chemistry could flourish, laying the groundwork for, or even becoming, life. While mainstream science acknowledges that organic molecules can form through abiotic processes, their discovery in ancient, water-rich environments like Jezero Crater's lake beds significantly elevates the possibility of a biological origin. The presence of these organic compounds also strengthens the panspermia hypothesis. If life did arise in these ancient Martian lakes, an asteroid impact could have ejected fragments of these mudstones, laden with organic material or even dormant microbes, into space. We know such transfer is possible. Meteorite analysis confirms we have over 200 Martian meteorites on Earth that endured the journey. These Martian travelers could have seeded Earth when it finally became habitable, making us perhaps the ultimate descendants of these ancient Martian organisms. As you watch the drill retreat, bringing forth a core sample of this profound mudstone, you sense the immense weight of the secrets it might still hold. You are in a pristine laboratory, the air sterilized and cool, yet a faint, almost imperceptible scent of ozone seems to cling to the air as you examine a Martian rock core. This core, extracted from the ancient floor of Jezero Crater by the Curiosity rover, is not just stone, it's a profound archive. You peer at its delicate striations, a geological narrative stretching back billions of years. Planetary science reveals this core is rich in clay minerals and sulfates, direct evidence that the rock formed in the presence of sustained liquid water. The subtle scent, perhaps a metaphor for pristine ancient air or a faint chemical echo, brings a sense of stepping into a primeval past. Geological evidence proves that these hydrated minerals require long-term interaction with water to form. Rover data indicates that the specific types of clays found within these mudstones are excellent at preserving organic matter. This is why Curiosity's discovery of complex organic molecules within these very clay-rich mudstones was so significant. It wasn't just water, it was the right kind of water, in the right kind of environment for life's building blocks and potentially life itself to emerge and be protected. This particular sample, imbued with the ghost of water and the potential for ancient organics, powerfully supports the timeline paradox. It speaks of an early Mars, cool enough for widespread liquid water, equipped with a thick atmosphere, proven by atmospheric isotope ratios, and a stable surface for hundreds of millions of years. This was a critical period, approximately 4 to 3.5 billion years ago, when Earth remained a largely molten, hostile sphere, bombarded by asteroids and too hot for stable liquid water. Mars had a 500 million year head start on habitability, a fertile window for abiogenesis. If life indeed arose in these ancient Martian aqueous environments, then the mechanism of panspermia becomes startlingly real. You consider how an asteroid impact could have ejected a fragment of this very clay-rich rock, laden with organic compounds or even dormant microbes, into space. Meteorite analysis confirms that Martian rocks have survived this journey to Earth. If life existed on early Mars, some of it could have been transferred, arriving on Earth when our planet finally cooled enough to offer its own pristine, competitor-free environment. As you carefully observe this ancient Martian sample, you are left to ponder, are we merely studying geology, or are we examining the very cradle of life, a cradle that might also be our ancestral home? You stand amidst the silent, dust-swept expanse of Jezero Crater, the faint Martian light painting the ancient landscape in shades of ochre and rust. You observe the dramatic topography, a sprawling river delta meticulously preserved for billions of years, now a testament to a liquid past. Imagine the immense feat of engineering that allowed the Perseverance rover to land with such precision in this geologically complex, yet scientifically rich environment. This wasn't just a landing, it was a pinpoint arrival at one of Mars's most promising sites for finding definitive evidence of ancient life. Planetary science reveals that Jezero Crater once hosted a deep, expansive lake fed by a mighty river that carved channels through its rim and built this impressive delta. Geological evidence proves the delta's existence and the long-term stable presence of liquid water for thousands to millions of years, approximately 3.8 to 3.5 billion years ago. This specific type of environment, where a river carried sediments, nutrients, and potential microbial life into a calm lake, is considered an ideal trap for preserving biosignatures, the fossilized remnants or chemical traces of ancient organisms. This carefully chosen landing site directly addresses the timeline paradox. During the era when Jezero Crater was a thriving lake, early Earth was still a largely molten sphere, constantly bombarded by asteroids, with surface temperatures too high for stable liquid water. Mars, being smaller, cooled and solidified faster, granting it a crucial 500 million to 1 billion year head start on habitability. Thus, Perseverance is exploring a world that was a potential cradle for life long before our own planet was ready. Rover data, through Perseverance's advanced instruments, is systematically collecting rock and regolith samples from this ancient delta. These precious samples are destined for eventual return to Earth, where laboratories can conduct far more sensitive and detailed analyses than any rover can perform in situ. The hope is to find unambiguous proof of ancient Martian microbes, or at least the complex organic molecules that would strongly suggest their past presence. If life did exist in Jezero's waters, the panspermia hypothesis suggests that asteroid impacts could have ejected these very delta sediments, carrying Martian microbes to Earth. Here, in this ancient delta, we might be on the verge of finding not just alien life, but our very own cosmic ancestors. You kneel within the ancient river delta of Jezero Crater, your gaze drawn to the incredibly fine, almost paper-thin layers of silt that compose its eroded banks. The air is still, carrying the faint scent of mineral dust as you contemplate these delicate geological records. Planetary science reveals that these fine-grained sediments were once deposited by the slow, steady flow of an ancient Martian river emptying into a vast, long-lived lake. Imagine the soft deposition of these silts, gently settling over countless millennia, creating an unparalleled environment for preserving the most fragile traces of life. Geological evidence proves that such fine-grained sediments, often rich in clay minerals, are ideal archives for organic matter and even fossilized microbes. On Earth, our earliest signs of life are often found within similar ancient mudstones and shales. Rover data indicates that the Perseverance mission is specifically targeting these clay-rich areas within the Jezero Delta, meticulously collecting samples for eventual return to Earth. The hope is that within these paper-thin layers, untouched for billions of years, lie the unequivocal biosignatures, perhaps even microfossils, of ancient Martian life. This focus on the delta's fine silt is critical to the timeline paradox. Early Mars, with its thick atmosphere and liquid water, including this very lake system that persisted for thousands to millions of years, was a fertile cradle for life approximately 3.8 to 3.5 billion years ago. During this same epoch, Earth was still a hostile, molten sphere, frequently bombarded, its surface temperatures far too high for liquid water stability. Mars had a 500 million to 1 billion year head start on habitability, a vast window for life to emerge and potentially form extensive microbial mats that, once buried, could be exquisitely preserved in these silty layers. If such microbial mats existed, the panspermia hypothesis gains even greater weight. You envision an ancient asteroid impact on this wet, life-rich Mars, ejecting fragments of these very delta sediments. Within the interior of these ejected rocks, encased in the protective silt, dormant microbes could have survived the millions of years' journey to Earth. Meteorite analysis has proven that Martian rocks have reached our planet. Here, in these delicate layers of Jezero Crater, we are not just looking for alien life, but perhaps the primordial source that seeded our own world, a profound connection to a deep cosmic past. You stand beside a rover on the vast, silent plains of Mars, feeling a faint, rhythmic vibration through the metal as its ground-penetrating radar hums to life. Invisible pulses penetrate the dusty Martian surface, revealing a hidden world beneath. You watch the screen, which flickers with abstract patterns, painting a subsurface portrait of layered bedrock, possible ice deposits, and the ghost of geological features buried for eons. This remarkable technology allows us to peer beyond the desiccated surface into the deep past of a planet that once held immense promise for life. Planetary science reveals that Mars, being smaller, cooled and solidified faster than Earth. During its critical early period, approximately 4 to 3.5 billion years ago, it possessed a thick atmosphere, proven by atmospheric isotope ratios, and was a warm, wet world. Geological evidence proves rivers flowed, lakes stood, and oceans may have covered vast northern plains. While Earth was still a hostile, molten sphere, Mars had a 500 million to 1 billion year head start on habitability. The ground-penetrating radar probes these depths, searching for structures or signatures preserved from that fertile era, undisturbed for billions of years. Within these buried layers, shielded from harsh surface radiation and the solar wind that stripped away the atmosphere, lie the best chances of preserving biosignatures, the fossilized remnants or complex organic molecules of ancient Martian microbes. Rover data, though not directly from GPR for biosignatures, complements this by showing surface evidence of past water. If life emerged and thrived here, it might have retreated to subterranean refuges as the surface became increasingly uninhabitable. The GPR could reveal these subsurface pockets or even ancient water reservoirs. This technological gaze into the unseen depths also fuels profound, albeit controversial, speculation. If Mars hosted life for 1 billion years before Earth, could intelligence have evolved? While mainstream science attributes controversial surface features to natural geology, the search beneath the surface, with tools like GPR, opens a new dimension for investigation. You ponder if the radar signals could ever reveal geometric patterns or unusual structures far beneath the regolith, challenging our current understanding. Ground-penetrating radar transforms Mars from a barren landscape into a multi-layered archaeological site, compelling us to uncover its deep, hidden truths and perhaps our own ancient origins. You descend, not physically, but in thought, far beneath the frigid, desolate surface of Mars. You imagine leaving behind the thin carbon dioxide atmosphere and the dust-swept plains, plunging into the black, unyielding rock. Here, in the hypothetical warmth of a geothermal vent, deep beneath the icy crust, liquid water might still flow. You picture shimmering plumes rising from cracks in the rock, carrying dissolved minerals and chemical energy, an oasis of potential life in a world otherwise frozen solid. Planetary science reveals that even as Mars lost its thick atmosphere and global surface water billions of years ago, a catastrophic event after its magnetic field collapsed, allowing solar wind to strip its protective blanket, its internal heat would have persisted. Geological evidence proves that Mars, like Earth, had a geologically active past. This suggests that hydrothermal systems, similar to those that host life in Earth's deep oceans and subsurface, could have existed and potentially still exist beneath the Martian surface. These deep, warm, wet environments represent prime refuges where life, if it arose during Mars's 500 million to 1 billion year head start on habitability, could have retreated and endured. This hidden world offers a profound perspective on the timeline paradox. Early Mars during its fertile epoch was a warm, wet planet, ideal for life to emerge. If that life adapted to the changing conditions, retreating underground, then our current search for methane fluctuations by rovers like Curiosity takes on even greater significance. Rover data indicating seasonal methane spikes could be a whisper from these deep, unseen biological communities, metabolizing and thriving in the sustained warmth of geothermal vents. The implications for panspermia from such enduring deep life are striking. If Mars had a persistent subsurface biosphere, asteroid impacts might still eject fragments from these deeper layers, increasing the chances of viable microbes surviving the journey to Earth. Mainstream science widely accepts the overwhelming evidence for early habitable Mars and the plausibility of ancient microbial life. The lingering question is whether life, perhaps sustained by these very geothermal vents, persists today. As you contemplate the hidden warmth beneath the Martian ice, you wonder, are we just searching for fossilized traces, or could a living, ancient Martian lineage still endure, whispering clues about life's ultimate resilience, and perhaps our own origins? You walk across the sun-baked, bone-dry expanse of the Atacama Desert in Chile, feeling the arid wind whisper past your face, kicking up fine, reddish dust. The landscape here, with its extreme dryness, high radiation levels and oxidized soils, is eerily similar to the surface of Mars, making it a crucial analogue for astrobiological research. This stark, beautiful environment offers invaluable insights into where and how life might persist in the most extreme conditions, even on a planet like Mars, now cold and barren. Planetary science uses these terrestrial analogues to develop and test instruments and to understand the limits of life. Despite the brutal conditions of the Atacama, life persists. Specialized microbes and extremophiles cling to existence, often finding refuge beneath rocks, within salt crystals, or deep underground where meager moisture or unique chemical gradients allow them to survive. This tenacious survival in Earth's Mars-like environments suggests that if life arose on early Mars during its 500 million to 1 billion year head start on habitability, it too might have found ways to endure, even after the planet's catastrophic atmospheric loss. The Atacama acts as a living laboratory for the timeline paradox. Early Mars, from 4 to 3.5 billion years ago, was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios, and flowing rivers, unlike the hostile, molten Earth. If life blossomed then, the Atacama demonstrates that a retreat to protected niches is a viable strategy for survival through planetary desiccation. This leads to the profound implication that even today, deep beneath the Martian surface, perhaps near geothermal heat sources, pockets of ancient microbial life could still exist, mirroring the hidden life found in Earth's driest deserts. This enduring possibility strengthens the panspermia hypothesis. If life on Mars persisted in these protected zones, even after its surface became uninhabitable, it increases the window for life to be ejected from Mars and transferred to Earth. Martian meteorites, like ALH84001, already proved that rock transfer is possible. The Atacama, therefore, becomes not just a testing ground for rovers and scientific theories, but a potent symbol of life's incredible resilience. As you survey the seemingly lifeless desert, you realize that even in the most desolate corners, life finds a way, offering a profound hope for the secrets that Mars may yet reveal about our cosmic family tree. You are deep underground, in the oppressive, lightless depths of Mobile Cave in Romania. The air is heavy with hydrogen sulfide, the walls drip with sulfuric acid, and the atmosphere contains 10 times less oxygen than on the surface, yet you feel a faint, humid warmth and see strange, pale creatures, spiders, centipedes, and unique microorganisms thriving in this seemingly impossible environment. This is a chemotrophic ecosystem, entirely cut off from the sun's energy, drawing sustenance from chemical reactions in the rock. Mobile Cave is a profound analogue for potential subsurface life on Mars. Planetary science considers such extreme terrestrial environments vital for understanding the resilience of life and its potential to persist in subterranean refuges on other worlds. The existence of a complex food web in Mobile Cave, driven by chemosynthesis rather than photosynthesis, mirrors the theoretical conditions that could exist deep beneath the Martian surface. If life arose on early Mars during its 500 million to 1 billion year head start on habitability, it could have adapted to the planet's atmospheric loss and retreated to similar underground sanctuaries. The early Mars, from 4 to 3.5 billion years ago, was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios and extensive liquid water. Geological evidence confirms rivers flowed and lakes stood. As the planet desiccated and its magnetic field collapsed, exposing the surface to deadly radiation, life could have found refuge in subsurface aquifers, sustained by internal geothermal heat and chemosynthetic processes. The thriving ecosystem of Mobile Cave serves as a powerful testament to how life, once established, can adapt to the most extreme changes, moving into the hidden depths of a dying world. This analogy directly informs the ongoing search for life on Mars. Rover data from Curiosity's methane fluctuations and the discovery of organic molecules in ancient mudstones, combined with the extreme resilience of Earth's subsurface life, make the possibility of extant Martian microbes scientifically plausible. Such a subsurface biosphere would also amplify the panspermia hypothesis, increasing the potential for Martian life to be ejected from deeper rock layers and transferred to Earth. As you feel the strange, humid air of Mobile Cave, you're not just exploring an earthly anomaly, but contemplating a profound truth about life's enduring will, and the very real possibility that Mars still holds living secrets, perhaps even a distant relation to ourselves. You are in a virtual clean room, bathed in the glow of monitors, witnessing a pivotal moment in astrobiology. The sample analysis at Mars, or SAM instrument, aboard the Curiosity rover, is performing its meticulous work. A small amount of powdered rock, drilled from a 3 billion year old mudstone in Jezero Crater, is heated in SAM's miniature oven. You watch the spectral readouts, a complex dance of peaks and troughs, and then it happens. Distinct signals confirming the presence of complex organic molecules, specifically theophanies, benzene, toluene, and small carbon chains. A profound silence falls, followed by a surge of excitement. This was a groundbreaking discovery. Rover data indicates that these organic molecules, the chemical building blocks of life, were preserved within a rock that formed in an ancient Martian lake. Planetary science reveals that these mudstones, rich in clay minerals, acted as excellent geological archives, protecting these delicate compounds from the harsh surface radiation and oxidation that Mars experienced after losing its protective atmosphere. Geological evidence proves that liquid water was abundant in Jezero Crater during this period, enhancing the potential for these molecules to be associated with past life. This detection of indigenous Martian organics directly addresses the timeline paradox. Early Mars, during the period when these mudstones formed, was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios, capable of sustaining lakes and rivers. This was 1 billion years before Earth fully stabilized and developed its own robust biosphere. Mars had a 500 million to 1 billion year head start on habitability a critical window for life's genesis. While organic molecules can form abiologically, their presence in such a clearly habitable environment makes the biological hypothesis compelling. The implications for panspermia are significant. If life arose on early Mars, these organic rich mudstones could have been ejected by asteroid impacts, traveling to Earth carrying the essential ingredients, or even dormant forms of life. Meteorite analysis confirms that Martian rocks have reached Earth, proving the mechanism. As you contemplate the spectral signatures on the screen, you realize that the SAM instrument, in detecting these ancient Martian organics, has opened a profound chapter in our understanding of life's potential universality and our own enigmatic connection to the red planet. You now contemplate the very atoms of existence, following the invisible cosmic journey of carbon. Having witnessed the detection of complex organic molecules within ancient Martian mudstone by the Curiosity rover's SAM instrument, your mind expands to the incredible odyssey these fundamental building blocks might undertake across the solar system. You imagine these carbon atoms, once part of a pristine Martian lake, perhaps incorporated into the earliest microbial life, now scattered, some trapped in rock, some freed by ancient solar winds. Planetary science reveals a profound interconnectedness between celestial bodies. Early Mars, from 4 to 3.5 billion years ago, was a water-rich world with a thick atmosphere, proven by atmospheric isotope ratios, making it a veritable crucible for organic chemistry. Rover data indicates the presence of not just water, but clay minerals which act as excellent preservers of these delicate carbon compounds. During this critical era, Mars had a 500 million to 1 billion year head start on habitability compared to Earth, offering ample time for simple organic molecules to evolve into the complex polymers necessary for life. The cosmic journey of carbon atoms, therefore, becomes intimately linked to the panspermia hypothesis. Imagine an asteroid impact striking this early, fertile Mars, ejecting rock fragments laden with these organic molecules or even dormant microbes encased within. Meteorite analysis confirms that Martian rocks have indeed survived millions of years in space, eventually landing on Earth. These molecular pilgrims, shielded within their rocky vessels, could endure the vacuum, radiation, and fiery atmospheric entry. If these carbon-based compounds, found in Martian mudstones, were part of a nascent Martian biology, then their journey to Earth implies a truly profound origin story. Earth, then a hostile, molten sphere, would eventually cool enough to receive these Martian gifts, finding a pristine environment with no biological competition. Thus, the carbon in our own bodies, the very essence of life on Earth, might share an ancient, common ancestor that first arose on the red planet. As you contemplate the cosmic ballet of carbon, from Martian lake beds to Earth's nascent oceans, you wonder, are we merely made of stardust, or are we, quite literally, made of Martian dust? You float silently above Mars, gazing down into the immense, majestic canyon system of Valles Marineris. It stretches for thousands of kilometers, dwarfing Earth's Grand Canyon, a colossal scar across the face of the red planet. Its sheer scale and dramatic geological features tell a story of immense tectonic forces, volcanic activity, and, crucially, the powerful erosive force of water over eons. You observe the layered rock exposing vast swathes of Martian history, a profound geological timeline laid bare. Planetary science reveals that while Valles Marineris was primarily formed by tectonic activity and volcanic processes, the evidence of past water within its many chasmata is compelling. Geological evidence proves the presence of hydrated minerals, signs of ancient lakes, and even channels that suggest catastrophic floods once coursed through its depths. This canyon system, a natural geological cross-section, offers invaluable insights into the subsurface conditions of early Mars, a world that was warm, wet, and potentially habitable. This ancient history directly impacts the timeline paradox. During the era when these water features were active within Valles Marineris, from 4 to 3.5 billion years ago, Earth was still a hostile, largely molten sphere, constantly bombarded by asteroids and far too hot for stable liquid water. Mars, being smaller, cooled and solidified faster, giving it a 500 million to 1 billion year head start on habitability. The sheer depth and exposure within Valles Marineris mean that materials from this early, fertile period are more accessible for study, revealing clues about the potential for life. If life emerged and thrived in these ancient Martian waters, the geological evidence of prolonged water activity within Valles Marineris indicates a robust environment for its development. The deep canyons could have also provided shielded niches for life to retreat to as Mars lost its thick atmosphere, proven by atmospheric isotope ratios, and dried out. The panspermia hypothesis gains further weight as you consider the violent impacts that shape this very canyon, potentially ejecting fragments of life-laden rock into space. As you gaze into the vastness of Valles Marineris, you wonder if, within its ancient depths, there are whispers of life that could have ultimately seeded our own planet. You are suspended within the towering walls of Valles Marineris, Mars's Grand Canyon, feeling the immense scale of its geological history. Your gaze is fixed on the exposed strata, layers of rock carved out over billions of years. You meticulously examine specific features, darker, staining patterns, recessed alcoves, and distinctive mineralogical signatures that planetary science interprets as the remnants of ancient water seeps and springs. These are not ephemeral flows, but evidence of sustained groundwater activity, persisting long after surface rivers dried. Geological evidence proves that these water-related features often contain minerals like sulfates and clays, which form in the presence of liquid water and are excellent at preserving organic materials or even fossilized microbes. These seeps represent potentially protected habitats, buffered from the harsh surface radiation and atmospheric loss that turned Mars into a frigid desert. Such environments could have harbored life that arose during Mars's 500 million year head start on habitability, allowing it to endure even as the planet transitioned. The exposed canyon walls of Valles Marineris provide a unique natural laboratory, offering access to strata that would otherwise be kilometers underground. This window into Mars's deep geological past directly informs the timeline paradox. A Mars with persistent subsurface water activity, a world that was warm and wet, existed when Earth was still a hostile, molten sphere. If life blossomed in these early Martian environments, these seeps could have been vital refuges, allowing it to adapt and survive for immense periods. If ancient Martian microbes thrived in these sustained water seeps, then the panspermia hypothesis becomes even more compelling. An asteroid impact could have ejected fragments of these very water-altered rocks, carrying life-laden material from Valles Marineris. Meteorite analysis confirms that Martian rocks have reached Earth, proving the transfer mechanism is possible. These deep-seated organisms, shielded from surface conditions within the rock, could have survived the millions of years' journey, arriving on Earth when our planet finally became hospitable. As you hover near these ancient water seeps, you ponder the immense resilience of life and the profound possibility that the origins of our own existence might be intricately tied to these deep, hidden, watery realms of Mars. You stand on the vast, desolate plains of Mars, witnessing a sunrise that paints the sky in subtle hues of butterscotch and blue. Before you, a long, impossibly vast shadow stretches for hundreds of kilometers, cast by Olympus Mons, the solar system's largest volcano. Its sheer, breathtaking scale rising 25 kilometers, 16 miles, above the surrounding plains, dwarfs anything on Earth. This colossal geological feature is a testament to Mars's active, fiery past, and its sustained geological activity plays a crucial role in understanding its potential for life. Planetary science reveals that Olympus Mons, a shield volcano, grew steadily over billions of years, a testament to a long-lived hotspot in Mars's mantle and the absence of plate tectonics. Geological evidence proves its immense size indicates a prolonged period of volcanic activity which would have released significant amounts of gases and water vapor into the early Martian atmosphere. This outgassing, contributing to Mars's once-thick atmosphere, proven by atmospheric isotope ratios, was essential in creating the warm, wet conditions necessary for liquid water to persist on the surface, supporting the timeline paradox. The presence of such colossal volcanic activity also suggests the existence of internal heat sources, crucial for potential subsurface hydrothermal systems. While early Mars, 4 to 3.5 billion years ago, was a world of rivers and lakes on its surface, the sustained heat from deep within, possibly driving geothermal vents, could have provided refuges for life as the surface became progressively harsher. These subsurface environments, shielded from radiation after Mars lost its magnetic field, could have sustained microbial communities even as the planet dried out. If life arose on early Mars during its 500 million to 1 billion year head start on habitability, such volcanic activity would have offered both the raw materials and energy for its genesis and survival. The immense forces involved in forming Olympus Mons also highlight the potential for powerful asteroid impacts capable of ejecting life-laden rock fragments into space, reinforcing the panspermia hypothesis. Meteorite analysis confirms Martian rocks have reached Earth, proving the possibility of transfer. As you gaze at the long shadow of Olympus Mons, a monument to a powerful ancient Mars, you wonder about the deep connections between planetary geology, life, and the potential origins of our own existence. You stand on the immense, frozen slopes of Olympus Mons, the air thin and frigid. Though outwardly stark and barren, you perceive subtle geological features, lobate debris aprons and distinctive textures that planetary science reveals are the telltale signs of ancient glaciers, now hidden beneath a protective layer of dust and rock. Imagine colossal rivers of ice, once slowly carving paths down this titanic volcano, holding vast reserves of water even as Mars's surface began to dry. Geological evidence proves that these features point to significant water ice deposits, preserved for billions of years, often just beneath the surface. This ice is a crucial component in understanding Mars's potential for life, both in its past and possibly its present. During its early history, approximately 4 to 3.5 billion years ago, Mars was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios and flowing rivers. It had a critical 500 million to 1 billion year head start on habitability compared to Earth, which was still a hostile, molten sphere. As Mars slowly lost its magnetic field and its thick atmosphere was stripped away by solar winds, its surface water largely vanished. However, the presence of these ancient glaciers suggests that significant water could have persisted, locking away moisture and creating unique, stable subsurface microclimates. If life arose on early Mars during its fertile period, these buried ice deposits could have provided long-term refuges for microbial communities, protecting them from radiation and desiccation. The preservation of water in these hidden glaciers also strengthens the panspermia hypothesis. Imagine an asteroid impact striking these ice-rich slopes, ejecting fragments of rock and ice into space. Within the ice, dormant microbes could have been shielded from the harsh cosmic environment, surviving the millions of years' journey to Earth. Meteorite analysis confirms that Martian rocks have reached our planet, proving such transfer is possible. As you gaze at the shadowed slopes of Olympus Mons, contemplating its hidden ice, you ponder if these ancient reserves are not just frozen water, but also frozen archives of life, waiting to reveal a profound truth about our own cosmic ancestry. You are in orbit above Mars, watching the mesmerizing seasonal dance of carbon dioxide frost over its polar caps. As Mars leans into its winter, vast expanses of the poles are covered in a shimmering, ephemeral layer of frozen carbon dioxide, or dry ice. Then, as spring arrives, this frost sublimates, turning directly from solid to gas, creating dramatic dark spots, spiders, and geysers that carve intricate patterns into the ice. This dynamic process, driven by Mars's tilt and orbit, offers a stark visual reminder of the planet's drastically changed atmosphere. Planetary science reveals that the current thin Martian atmosphere is dominated by carbon dioxide. The cyclical freezing and sublimation of this gas at the poles play a significant role in the planet's climate dynamics today. However, this is a vastly different atmosphere from the one early Mars possessed. Geological evidence proves that Mars once had a much thicker, warmer atmosphere, sustained by a magnetic field that later collapsed. Atmospheric isotope ratios confirm that Mars lost most of this early atmosphere to the solar wind over millions of years, leaving it cold and dry. This atmospheric mystery is central to the timeline paradox. Early Mars, approximately 4 to 3.5 billion years ago, experienced a warm and wet period precisely when Earth was still a hostile, molten sphere. Mars had a 500 million to 1 billion year head start on habitability. Its thick atmosphere and abundant liquid water, including rivers, lakes, and possibly oceans, creating ideal conditions for life to emerge. The dramatic loss of this atmosphere turned Mars into the planet we see today, a world where water can now only exist stably as ice or vapor. If life arose on early Mars during its habitable epoch, the atmospheric loss would have profoundly impacted its survival, likely forcing it into subsurface refuges. The potential for such life to have been ejected from Mars through panspermia, carried on meteorites like ALH84001, becomes even more intriguing when considering the conditions of that ancient, thicker atmosphere. As you watch the seasonal dance of carbon dioxide frost, you are witnessing the aftermath of a planetary tragedy, a profound transformation that forever altered Mars's destiny, yet perhaps seeded Earth with its own unique legacy. You stand before a magnificent, exposed cross-section of Mars's polar ice cap, its layers glowing with ethereal blue and white. This is not just frozen water, it is a meticulously preserved chronicle of billions of years of Martian climate history, etched in layers of water ice and dust. You run your gaze over the intricate stratifications, each band representing a distinct epoch, a silent testament to the planet's dramatic environmental shifts, from a warm, wet past to its present cold, arid state. Planetary science reveals that these polar layer deposits contain vast quantities of water ice, kilometers thick. Geological evidence proves that these layers formed over immense timescales, accumulating dust and ice, preserving a pristine record of past atmospheric conditions, orbital wobbles, and even ancient precipitation events. By analyzing the composition and thickness of these layers, scientists can reconstruct Mars's ancient climate, peering back to the very period when it was most habitable. This profound archive directly informs the timeline paradox. Early Mars, approximately 4 to 3.5 billion years ago, experienced a warm and wet period, complete with a thick atmosphere, proven by atmospheric isotope ratios, and abundant liquid water. During this era, Earth was still a hostile, molten sphere. Mars had a 500 million to 1 billion year head start on habitability, a golden age for life's potential emergence. The polar ice caps, while formed later, contain remnants of that water, chemically preserved, offering clues about its composition and the conditions of its ancient environment. If life arose on early Mars and those ancient Martian microbes were incorporated into ice or dust that later formed these layers, then these ice cores could be literal time capsules preserving biosignatures. The layers might hold chemical traces of past biological activity or even dormant cells. This possibility, combined with the proven mechanism of panspermia, where Martian meteorites like ALH84001 reach Earth, suggests a profound cosmic connection. As you study these ancient layers of ice, you are not just reading climate history, but contemplating a fundamental truth: that the cold, still beauty of Mars's polar caps might hold the key to understanding our own living past, a past perhaps shared across the solar system. You witness a cataclysmic event unfolding on ancient Mars. An asteroid, a behemoth of rock and ice, screams through the thick Martian atmosphere, a fiery streak against a primeval sky. With an unimaginable roar, it slams into the planet's surface, carving a vast crater. The ground trembles violently, seismic waves rippling outward. You watch as immense plumes of debris, superheated and pulverized rock, are blasted into the void of space, escaping Mars's gravitational pull. This is the dramatic, violent mechanism behind panspermia, the cosmic transfer of life. Planetary science reveals that such impacts, while devastating locally, are powerful enough to eject rocks from Mars at velocities exceeding escape velocity. Geological evidence proves that Mars endured a period of intense bombardment in its early history, precisely during the era when it was a warm, wet world. This was the critical period, 4 to 3.5 billion years ago, when Mars had a 500 million to 1 billion year head start on habitability compared to Earth, which was still a hostile, molten sphere. It was also during this time that life could have emerged and taken root. These ejected rocks, now meteorites, embark on journeys lasting millions of years through the vacuum of space. Meteorite analysis confirms that over 200 Martian meteorites have been identified on Earth, proving this interplanetary transfer is entirely possible. Crucially, studies have shown that microbes can survive the shock of impact ejection, the freezing radiation of space while shielded within rock interiors, and even the fiery descent through Earth's atmosphere. If life existed on early Mars, then these asteroid impacts become profound cosmic gardeners, capable of seeding other worlds. Imagine a fragment of Martian rock, perhaps from an ancient riverbed or lakebed like Jezero Crater, containing dormant Martian microbes. Propelled by an impact, it hurtles towards Earth, eventually arriving when our planet had cooled enough for liquid water and a stable surface. This mechanism suggests that Earth's earliest life might not have originated here, but could be a direct descendant of those intrepid Martian travelers. As you contemplate the raw power of the asteroid impact, you realize it is not just a force of destruction, but a potent ancient pathway for life itself. You are now a silent observer in the cold, vast emptiness of space, watching a dark, irregularly shaped rock on an impossible journey. This is a Martian meteorite, propelled from its home planet by an asteroid impact billions of years ago. It tumbles through the void, bathed in the harsh radiation of the sun, enduring unimaginable temperatures. This is the heart of the panspermia mechanism, the incredible long, cold journey of a rock potentially seeded with life towards a young Earth. Planetary science proves that such journeys are not merely theoretical. Meteorite analysis confirms that over 200 known Martian meteorites have been discovered on Earth. Some, like ALH84001, containing organic compounds and structures resembling fossilized bacteria. These rocks demonstrate that planetary material can indeed be transferred between worlds, a vital prerequisite for panspermia. Studies show that microbial life, particularly extremophiles, can survive the shock of impact, the vacuum of space while shielded within rock, and even the intense heat of atmospheric entry. Imagine the origin point of this journey. An early Mars, approximately 4 to 3.5 billion years ago. This was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios and flowing rivers and lakes, such as those found in Jezero Crater. Mars had a critical 500 million to 1 billion year head start on habitability compared to Earth, which was still a hostile, molten sphere, frequently bombarded and far too hot for stable liquid water. If life emerged on Mars during this fertile epoch, these rocks could have been its interstellar emissaries. This ancient Martian meteorite, perhaps carrying dormant spores or preserved organic blueprints, would travel for millions of years. Eventually, guided by gravitational forces, it would fall through Earth's nascent atmosphere, a fiery descent survived by its core. Landing in Earth's primordial oceans, it would find a pristine, competition-free environment, ready for the seeds of life. This scenario proposes that Earth's life may not be indigenous, but rather descended from Mars. As you witness this cosmic voyage, you realize the immense philosophical implications. Are we searching for alien life on Mars? Or are we searching for our own ultimate ancestors, transported on these ancient, intrepid rocks? You are in a sterile clean room, the air filtered to an unimaginable purity, the silence broken only by the hum of ventilation systems. Scientists, clad in pristine suits, meticulously handle delicate components. Here, the very sample collection tubes that Perseverance uses on Mars are forged, sterilized to an extreme degree to prevent earthly contamination. This meticulous process underscores the immense scientific and ethical responsibility of searching for alien life and preparing for sample return. Planetary science recognizes that finding definitive proof of ancient Martian life is paramount. The samples collected by Perseverance from Jezero Crater, an ancient river delta and lake bed, are specifically chosen for their high potential to preserve biosignatures. Geological evidence proves that these environments hosted long-term stable liquid water for thousands to millions of years, approximately 3.8 to 3.5 billion years ago. During this epoch, early Mars was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios, a stark contrast to the hostile, molten Earth of the same period. Mars had a crucial 500 million to 1 billion year head start on habitability. The rigorous process of creating these sterile sample tubes directly addresses concerns about contamination, which plagued earlier missions, and the interpretation of meteorite analysis like ALH84001. When these Martian samples finally return to Earth, they will be subjected to analyses far more sensitive and diverse than any rover could perform, allowing scientists to look for complex organic molecules, isotopic fractionations, or microscopic fossil structures that could unequivocally prove ancient life. If these returned samples reveal definitive proof of life, the philosophical implications are staggering. If life arose independently on Mars before Earth, it would suggest that life emerges readily under the right conditions, implying the universe might teem with living worlds. And if that Martian life eventually seeded Earth through panspermia, then we are, quite literally, Martians, descendants of those ancient microbes. As you observe the meticulous work in the clean room, you realize these tubes are not just containers. They are vessels of a profound hope, carrying the potential to rewrite our cosmic origin story. You are in a mission control room, not waiting for a landing, but for a departure, a future arrival. Before you, screens display intricate orbital mechanics and complex trajectories. The ambitious plan for the Mars sample return mission. This audacious endeavor aims to retrieve the precious rock and regolith cores collected by Perseverance in Jezero Crater and bring them safely back to Earth. You feel the weight of this undertaking, plotting the complex choreography required to bring a piece of Mars, potentially a piece of our past, home. Planetary science considers sample return missions the ultimate step in the search for ancient Martian life. While rover data and in situ analysis have provided tantalizing clues, like the organic molecules found by Curiosity or the structures in ALH84001, definitive proof requires the advanced analytical capabilities of terrestrial laboratories. Geological evidence proves that the Jezero Crater delta, with its long-term stable liquid water from 3.8 to 3.5 billion years ago, offers the best chance to find preserved biosignatures. The complexity of the mission reflects the profound implications of its success. This isn't just about collecting rocks, it's about retrieving a potential snapshot of Mars during its warm and wet era, a time when it had a 500 million to 1 billion year head start on habitability compared to a still molten Earth. If these samples contain undeniable proof of ancient life, it would not only confirm that life arose independently on another world, but also critically evaluate the panspermia hypothesis. Imagine studying Martian DNA, or a Martian microfossil here on Earth. The philosophical ramifications of finding life in these samples are immense. If life on Mars arose independently, it suggests life is common in the universe. If, however, that life seeded Earth through panspermia, then we are, quite literally, Martians, tracing our lineage back to the red planet. The Mars Sample Return mission, plotting its complex trajectory across the vastness of space, holds the potential to unlock our deepest cosmic origin story. As you watch the simulated flight paths, you ponder the incredible journey ahead, a journey that might soon deliver the most profound scientific discovery in human history. You are in a dimly lit office, the glow of distant city lights barely piercing the window. Two astrobiologists, their voices low and contemplative, engage in a late-night conversation, not about if life exists elsewhere, but about a second genesis on Mars. They speak of the tantalizing possibility that life arose independently on Mars before Earth, profoundly impacting our understanding of biology's prevalence in the cosmos. One scientist gestures to a holographic projection of early Mars, a vibrant, blue-tinged world. Planetary science reveals that Mars had a 500 million to 1 billion year head start on habitability. Geological timelines show it cooled faster, becoming a warm, wet world with a thick atmosphere and flowing water, proven by atmospheric isotope ratios and geological evidence of ancient rivers and lakes, while Earth was still a hostile, molten sphere. This early Mars from 4 to 3.5 billion years ago offered a prime environment for life's genesis. The discussion revolves around whether this was enough time for life to emerge completely independently, forming a unique second genesis of life in our solar system. The other scientist counters, presenting images of Martian meteorites like ALH84001, highlighting structures resembling fossilized bacteria and organic compounds. Meteorite analysis confirms these rocks made the journey to Earth. This brings the panspermia theory into sharp focus. If life arose independently on Mars, could it have then seeded Earth? This isn't just a second genesis, it's a first genesis elsewhere, leading to a transplant genesis on our own planet. The implications are staggering. Our DNA, our very biological blueprint, might be of Martian origin. The conversation acknowledges the current scientific consensus, overwhelming evidence for early habitable Mars and the plausibility of ancient microbial life, actively sought by rovers like Perseverance in Jezero Crater. But definitive proof of a second genesis, or of panspermia, remains the elusive prize. If found, it would demonstrate that life is not a rare cosmic accident, but a fundamental consequence of suitable planetary conditions. You listen, mesmerized by the quiet passion in their voices, recognizing the profound philosophical questions at stake. If life emerges readily, is the universe teeming? And if we are Martians, what does that mean for humanity's identity and future? You stand before a profound museum exhibit, The Origins of Life on Earth. Display panels chronicle the emergence of single-celled organisms, the rise of complex life, and the vast evolutionary tree that led to humanity. Yet, one space, conspicuously blank, is reserved for the first spark. It represents the ultimate question: where did life truly begin? You gaze at it, realizing that the answer might not solely reside on Earth, but on our red neighbor. This blank space exists because, despite overwhelming evidence for early habitable Mars, a world with flowing rivers, standing lakes, and a thick atmosphere, proven by atmospheric isotope ratios and geological evidence, 4 to 3.5 billion years ago, the question of life's first spark remains. Planetary science confirms that Mars had a critical 500 million to 1 billion year head start on habitability compared to Earth, which was still a hostile, molten sphere. This early window provides a compelling argument for life arising there first. Mainstream scientific consensus acknowledges that while proof of ancient Martian life is still elusive, the possibility that Mars hosted microbial life before Earth is considered scientifically plausible and is the primary driver of Mars exploration missions. Organic molecules, like those found by Curiosity, exist, but could be abiotic. Methane fluctuations might be geological. Yet the evidence supporting panspermia is growing. Meteorite analysis confirms that Martian rocks, some even containing structures resembling fossilized bacteria like ALH84001, have reached Earth. This proves that life could indeed travel between planets, potentially seeding Earth with Martian DNA. The implications for this blank space are profound. If upcoming sample return missions from Jezero Crater find definitive proof of ancient Martian microbes, we might fill that space not with life arose on Earth, but with life arose on Mars, then seeded Earth. This would redefine our origin story, making us Martians, explorers returning to our ancestral home. It would also suggest that life is not unique to Earth, but a robust phenomenon that readily emerges given the right conditions, implying the universe teems with life. As you reflect on the blank space, you recognize it as a symbol of humanity's ongoing quest, a profound mystery awaiting a revelation that could forever change how we view ourselves and our place in the cosmos. You are in a softly glowing server room, the rhythmic hum of a supercomputer filling the air. On the massive screens, lines of 40-year-old data, once dismissed as inconclusive, are being reanalyzed by a sophisticated new algorithm. This isn't raw rover data from a new mission. It's the very information gathered by the Viking landers in 1976, now re-examined with fresh eyes and advanced computational power. This technological leap offers a tantalizing chance to revisit Mars's oldest mysteries. Planetary science reveals the original Viking-labeled release experiment yielded a positive signal, suggesting metabolic activity in Martian soil. However, the absence of organic molecules in a companion experiment led mainstream science to attribute this to non-biological chemical oxidants. Yet, some researchers always maintained the possibility of a biological interpretation. Now, with new algorithms capable of discerning subtle patterns and complex chemical reactions, the old data is being scrutinized for nuances previously undetectable. Could this reanalysis finally resolve the ambiguity, proving a biological signal after all? This reassessment of Viking data connects directly to the timeline paradox. Early Mars, 4 to 3.5 billion years ago, was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios and geological evidence of ancient rivers and lakes. It had a critical 500 million to 1 billion year head start on habitability compared to Earth, which was still a hostile, molten sphere. If life did arise and persist on Mars, even in dwindling numbers by the Viking era, perhaps these new algorithms can uncover its faint, lingering trace. The implications for panspermia are significant. If these algorithms detect definitive biological markers in the Viking data, it would provide compelling evidence for extant life on Mars, reinforcing the idea that life emerges readily and can endure extreme planetary transformation. If life was present on Mars during its fertile past and potentially persisted, then the transfer of Martian microbes to Earth via meteorites, a proven mechanism, becomes a powerful theory for our own origins. As you watch the supercomputer tirelessly process the data, you are reminded that even old evidence, viewed through a new lens, can unlock secrets that redefine our cosmic understanding and perhaps even our identity. You are in the quiet hum of a contemporary research institution, the air filled not with Martian dust, but with the subtle static of unresolved questions. Before you, a screen displays the conflicting data from the 1976 Viking missions. The labeled release experiment's positive signal, hinting at life, starkly contrasted by the gas chromatograph mass spectrometer's non-detection of organic molecules. This enduring ambiguity, a scientific enigma spanning decades, continues to fuel a new generation of scientists, transforming doubt into the most potent form of inquiry. Planetary science reveals that the initial interpretation of Viking's results leaned towards abiotic chemical reactions, effectively closing the door on present-day Martian life. Yet, as rover data from later missions, like Curiosity, began to unearth more evidence of Mars's early, wet past, including complex organic molecules in 3-billion-year-old mudstones, the Viking anomaly became harder to dismiss. The very questions that led to its dismissal now resurface with renewed vigor. Was the GCMS sensitive enough? Were the oxidants truly the sole explanation? This lingering uncertainty is a powerful catalyst. This ambiguity deeply intertwines with the timeline paradox. Early Mars, from 4 to 3.5 billion years ago, was a warm, wet world with a thick atmosphere, proven by atmospheric isotope ratios and geological evidence of rivers and lakes, offering a critical 500 million to 1 billion year head start on habitability over Earth. If life arose and thrived then, could a faint, resistant lineage have persisted to the Viking era, perhaps in shielded subsurface niches, only to be missed or misinterpreted by nascent technology? The possibility that life on Mars had a long enough period to evolve and adapt adds weight to the unresolved Viking signal. The pursuit of definitive answers to this ambiguity directly drives current missions. Perseverance is meticulously collecting samples from Jezero Crater, an ancient river delta chosen for its potential to preserve robust biosignatures precisely to avoid such unresolved questions. If these samples or future reanalysis of old data definitively prove ancient Martian life, it would not only resolve the Viking ambiguity, but also solidify the panspermia hypothesis, that Earth's life could be descended from Mars, transported by meteorites like ALH84001. You consider this powerful, lingering ambiguity, realizing it's not a failure of science, but its ultimate engine, compelling us to search deeper for answers that might redefine our place in the universe. You stand on the dusty, rust-colored surface of Mars, the thin air carrying the faint whisper of ancient winds. Above you, in the Martian twilight, hangs a breathtaking sight. Earth, a distant, faint, blue dot, almost lost in the vastness of space. It is a profound, humbling image that encapsulates the entire mystery of our origins. For this tiny celestial pearl, teeming with life, may owe its very existence to the seemingly barren world beneath your feet. You gaze at that fragile blue dot, and planetary science reveals an incredible timeline. While that vibrant Earth was still a hostile, molten sphere, frequently bombarded by asteroids and too hot for liquid water, Mars, approximately 4 to 3.5 billion years ago, was a warm, wet world. Geological timelines show it cooled and solidified faster than Earth, giving it a crucial 500 million to 1 billion year head start on habitability. Geological evidence proves ancient rivers flowed, vast lakes stood, and a thick atmosphere, confirmed by atmospheric isotope ratios, protected its surface, creating conditions ideal for life to emerge. This stark contrast between early Mars and early Earth fuels the panspermia hypothesis, that life could have arisen on Mars first, then journeyed to our planet. You imagine an ancient asteroid impact on this fertile Mars, ejecting fragments of rock, perhaps from a life-rich river delta, like Jezero Crater or the organic-laden mudstones discovered by Curiosity. Meteorite analysis, specifically of over 200 known Martian meteorites on Earth, proves that such interplanetary transfer is entirely possible, even across millions of years, with microbes shielded within rock interiors. If life emerged on early Mars, then those ancient, intrepid microbes could have been passengers on these meteorites, arriving on a nascent Earth when it finally cooled enough to sustain liquid water. They would have found a pristine environment with no biological competition, a blank canvas upon which to paint life's intricate tapestry. This means that faint blue dot, our home, might be a direct descendant of the red dust beneath your feet. Are we searching for alien life on Mars? Or are we, in truth, searching for our own ancestors, the original Martians? You stand under the vast, silent Martian sky, the red dust settling around you. The faint blue dot of Earth, our home, hangs above. You reflect on the incredible journey of scientific discovery that has led us to this moment, a moment where the ancient history of Mars profoundly challenges our understanding of life's genesis. The evidence for early habitable Mars is overwhelming and accepted by the planetary science community. It was a warm, wet world with a thick atmosphere and abundant liquid water, proven by atmospheric isotope ratios and geological evidence of rivers and lakes, during a critical 500 million to 1 billion year period when Earth was still a hostile, molten sphere. The possibility that Mars hosted microbial life before Earth is considered scientifically plausible and is the primary driver of current Mars exploration. We are not asking, could Mars have had life? But where is the proof? Rover data, like Curiosity's organic molecule discoveries and methane fluctuations and the tantalizing structures in the ALH84001 meteorite, hint at a vibrant past. The panspermia transfer mechanism is proven possible. Martian rocks have reached Earth, demonstrating life could travel between worlds. This convergence of evidence presents profound philosophical implications. If life arose independently on Mars, it proves that life emerges readily given the right conditions, suggesting the universe teems with life. If Earth was seeded by Mars, then our lineage, our very DNA, is Martian. We are descendants exploring our ancestral home, an origin story far grander and more interconnected than previously imagined. And what if Mars not only hosted life first, but evolved it to intelligence before its catastrophic atmospheric loss? While mainstream science explains controversial features like the face on Mars as natural geology, the enduring timeline paradox, Mars's billion-year head start on habitability, allows for such contemplation. Did Martians see their world dying, attempt to preserve knowledge, or even perhaps deliberately seed Earth? As you look from the barren Martian surface to the distant living blue dot of Earth, a haunting question arises. Will Earth follow Mars's fate, warm and wet, becoming cold and dead? Mars stands as a cosmic cautionary tale and a potential genesis point. The quest for definitive proof continues, driven by our insatiable curiosity. What profound truths await us when the samples from Jezero Crater finally return? Are we seeking alien life, or are we seeking ourselves, etched into the red dust of Mars, a shared past, and a divergent, mysterious present?